So this is actually, thank you first of all for the invitation. It's an honor to be invited by both the DL and the NMR workshop to expose my work. And so this is work with a former PhD student of mine, Christos Ransoudis, who happens to give the next talk on a different subject. So this is basically about what he did during his PhD work, and we did it also together with a colleague, Guillaume Feuillade. And I'm going to talk about something which is important in databases, namely how to repair a database, and specifically about a proposal there, which is to have active integrity constraints. And I'm going to look at how this can generalize to description logics. So clearly integrity constraints are an important thing, and they should always be satisfied, but that's theory, but in practice they are often violated. Look at this example. It says that you cannot be a bachelor and married at the same time. And now you start from a database where John is a bachelor. You add that he got married and you get to an inconsistent state. So as a picture, you have this realm of good database states which satisfy the integrity constraints, and adding that John is married naively without withdrawing that he is a bachelor makes you go to that red violation state. So there are basically these two solutions which people have investigated. One is make the database great again or consistent again, which amounts to what people sometimes call data cleaning, throw out some things and add some things. And the other option is to live with inconsistency. So that's a sort of a hypothetical repair, and that's under the name consistent query answering a big topic also in description logics. So a consistent answer should hold in all possible repairs, because there can be more than one. There can also be zero. So if we go back to our example, the database that violates the integrity constraints can be repaired in many, many ways. We can kick out, we can reject the new piece of information, just stay with John is a bachelor, or we can make him married and kick out that he's a bachelor. But there are more than that, like DB3, there is some UFO, that Jim is a bachelor coming in. It also does the job of, again, satisfying the integrity constraints. But, well, there are more than that. There are clearly too many, and clearly some are not intended. So the first intuition people followed since long is that modification should be minimal. So if I have that realm of database state satisfying the constraint, and I start from DB0, I go out and go to a violating state, DB, then going back into the constraint satisfying database states, I should go either to DB1 or to DB2, but DB3 is definitely not close enough to the red DB. So what is a good definition of closeness? Well, symmetric difference in terms of databases being sets of atoms has been proposed since long in the 1988 by Winslet in a possible models approach. And that's why I call these repairs, although it's not standard in the literature, PMA repairs, because they bring exactly about PMA updates. So even if we have these PMA updates, the number of repairs can still be huge. And again, some of these are still unintended. For example, if you're a bachelor and then you get married, you can't get bachelor back again. So typically, the good repair is the second one. John got married, it was forgotten to withdraw or to kick out that he's a bachelor, but it should definitely go out. Now, how can we achieve that? Both DB1 and DB2 are inclusion minimal, set inclusion minimal, so they are PMA repairs. How can I make that DB1 is unintended? And one way of doing so is to make the constraints more informative. How can we do that? Well, at least in maybe earlier, but Fleska et al. In 2004 proposed active integrity constraints, which are not only static constraints, but they also have update actions which tell you how to repair that constraint, how to make it true again once it got violated. So for our example, if we have somebody who's a bachelor and married, that's not good, then we should withdraw that X is a bachelor. So what are the intuitions behind these rules? Because this looks nice, but they could clearly interact in complicated ways, and that's going to be the difficulty here. So the intuition is simply, well, we specify how to, again, satisfy a violated constraint, or more precisely, and that's where non-monotonic reasoning comes in, and look at Trushinsky, who proposed that formulation with Caro Prese. An active integrity constraint encodes explicitly both an integrity constraint and preferred basic actions to repair it if it is violated. Right? So this is actually based on some earlier work. In particular, I'm only going to talk about the first one, these active databases, since the 90s, or perhaps even earlier. They had something more complex, event condition action rules. So if an event occurs and some condition holds, then do some action. So the active integrity constraints actually don't have that event component. And the reason is that these ECA, event condition action rules, don't have declarative semantics, only procedural. And there are problems, repairs may not terminate. Basically, there's not too much of a consensus in the literature what the good semantics should be. And there are other predecessors, but I will skip them here. So what I would like to do in this talk is to sort of revisit the intuitions underlying these active constraints and also question them and which is the right semantics. And I will propose a dynamic logic analysis of these active constraints, which is actually similar to what people did in the SIT-calc a long time ago for the ICA rules. And finally, I will look at how this transfers to description logic. So let's revisit the basics. First of all, we need a little bit of notation. So we're going to work in propositional logic. That makes things a bit easier to present. So we suppose everything is grounded and that we are talking about a set of propositional variables with typical elements P and Q. Then databases are nothing but sets of propositional variables. Static integrity constraints, they are just clauses or sets of literals. And update actions are assignments of these propositional variables to true or false. So plus P makes P true, minus P makes P false. And a set of update actions is consistent if it doesn't do opposite things. If it doesn't try to add and to delete P. So now, with all that, we can define what is the update of a database by a set of update actions U. Well, the obvious thing, we delete what has to be deleted, we add what has to be added, and the order doesn't play a role if we have consistent update actions. So again, formally, the syntax is a couple. So an active integrity constraint, people like to talk about in terms of rules. Therefore, the R, it has that C of R, the clause part, the static integrity constraint part, and the repair part, which tells me how to repair the violation. So that is a set of update actions. And well, it should only make one of these literals true. So that's what is said by that concept. It is not that important. For example, if it is not the case that somebody is a bachelor, it cannot be the case that somebody is a bachelor and married, then you should delete bachelor, right? So now the objects we are looking at is not only databases, but databases augmented by finite sets of these active integrity constraints called eta. So which semantics for that? And Well, there's actually not too much consensus either. So there are many, many proposals, at least 6. Well, the first doesn't really count because these are the PMA repairs, but there are others with different behavior, and people mainly look at examples and how their proposal behaves on an example and does better than a previous proposal. And actually it's worse than that because each of these 5 semantics has several versions. So we may drop the minimality requirement, and then we get weak versions. So weak PMA repairs, which are nothing but drastic updates, but also weak founded repairs and so on. And we can also sort of allow exceptions. So we have these preferred repair routes, which are specified by the active constraint, but sometimes we allow to do something with it which is not really licensed, not really permitted by the active constraint. So we view these preferred update actions as soft constraints. And for that soft constraint version, repairs always exist as soon as the static part is consistent. So if we look at the intuitions behind, and that is not very explicit when you read the papers, but actually one can work out 2 different distinctions between two different readings of active integrity constraints. Namely, the first is a permission version. So if the static constraint is violated, then in that update part, in the active part with these assignment actions, then the repair should contain, or may contain rather, so it gets a permission to be in the repair. But we also allow that static constraint can be repaired in another way by some other active constraints. And the citation here has exactly that allowed keyword, which says that these authors view this as permissions. And the other one is obligations. So if the constraint is violated, then the repair must contain at least one of these update actions in the repair part of the active constraint. And that is, it's a longer citation, but that is supported by these authors, rather, it seems. So if we take that distinction serious, which consequences does it have? Well, first of all, if we adopt the permission reading and we have a constraint, an active constraint, like in this example, P or Q should be true, and then I can repair this by making P true or by making Q true. In the permission reading, this should be equivalent to these 2 constraints. If P or Q is violated, then I can make P true to repair it. If P or Q is violated, then I can make Q true to repair it. Yeah? So we can actually normalize the active part of an active integrity constraint and suppose that all these right-hand sides of active integrity constraints are singletons. And this contrasts with the obligation reading where this is not supported, because if I say if P or Q is, so look at the right rather, if P or Q is violated, then P plus P must be in the repair and plus Q must be in the repair, then both must be in the obligation reading. While this only forces me to have one in the repair. So no normalization for the obligation reading, and it also has a more local character than that permission reading. I don't have to look at the other active integrity constraints, whether they potentially repair something for me in order to check whether I have to apply an active constraint. Okay, so that is that permission obligation distinction, which I believe to be important, and we will see that some follow this and some of the other reading. But first of all, what does it mean that a constraint is violated? Does it just mean that a constraint is violated in the present database state, or could a violation occur during a repair process? Yeah. So that's not easy to work out. And what I will therefore do now is that I will go through 5 abstract, very simple examples in order to make our intuitions a bit clearer about this. So first of all, suppose we have only one violation and no interaction between the constraints. So in our example, the database is empty and the first active constraint says, yes, but P or Q should be true, and you can make P true or you can make Q true to go there, to repair that. And the second one says Q or not R should be true, and this one is, so the first one is violated, the second one is satisfied. Q or not R should be true, if not, make Q true. So the possible repairs are either making P true or making Q true. And the lesson to learn here is that if I have one violation and there's no interaction with the rest of the constraints, which basically means that the resolution rule does not apply, then just take all the update actions and each singleton is going to be a good repair. That is very intuitive. Yeah? Very simple case, only one violation. The repair will not interact with the rest of the constraints. Well, any of them is a minimum repair. Now, the next example, suppose we have a little bit of interaction. So we have one constraint which says that P must be true, and one says if P is true, then either Q or R must be true, and I prefer Q to be true. Then the repair obviously should be to make P true and to make Q true, and not to make R true, because R doesn't get a ticket for getting repaired here. But now observe that, first of all, only this one is violated, and the violation of the second one only occurs once I have applied the first one. So it is not enough a criterion to say that the static part of the repair should be violated in the current database. It could also be during the repair process, which means that we must have to hypothesize membership in the repair U, and then we get into problems such as circularity of support, which are not so easy to sort out. Okay, and actually up to now, I made that difference between the reading of permission and obligation. Up to now, we haven't seen whether that makes a difference, but here is an example where it makes. So empty database, again, P or Q should be true, make P true, P or Q should be true, make Q true. And then in the permission reading, the repairs should be plus P and plus Q. Each of them does the job. But the obligation reading has a single repair, making both P true and Q true. And that's actually not a minimal repair, so it's not a PMA repair. And we might, I believe, take this as a sign that the active part of the eta of these constraints, the active part is badly designed. I somewhat did too much. My next example is again about empty database, and very simple. P must be true, make P true. P or Q must be true, Q make Q true. The permission reading leads to plus Q, and because this is not minimal, the obligation reading, the only potential repair could be making both true, but that's not a PMA repair. So again, one may wonder whether the active constraints haven't been badly designed. Last example, I have, look only at the static part here on the left of these active constraints. I have something which says, look at the first two. P or Q should be true, P or not Q should be true. Actually, that's the same as P should be true. And for both, the repair is make P true. Now here, actually, I have intuitions which differ from those of Mirek Toshinsky and Gianno Caroprese, who say that this is not well designed. We have a circularity of support here, and it should not have a repair, this situation. In contrast, I would say that if I make both P and Q true, then this should be a good repair. And my argument for that is that we can apply a sort of extensionality principle, which is very reasonable, to these first two active constraints. So look at them again. Basically, the static part of these two constraints is equivalent to P, and they prescribe the same repair. So these first two active interrogatory constraints should be replaceable by simply P should be true, and if not, make it true. And then we can get back to the previous example where we had repairs in both cases. Yeah. Okay, so summarizing the intuitions that I tried to put forward, first of all, my first point was that one should distinguish a permission. One should be clear about whether one has a permission reading or an obligation reading, and they come with different intuitions. And actually my preferred one, which hasn't been investigated too much in the literature, is the obligation reading. My main reason for that is that it is more local. So it, it is more local and should lead to a simpler account. Second point, the obligation reading often leads to non-minimal repairs, but that might indicate a bad design of the active constraints. And my last point is that that extensionality principle, that seems very reasonable to me, and I think it leads to a more general criteria of identity for sets of integrity constraints. And one could also, so extensionality is one, could be viewed as a postulate, like in belief revision theory. One could look at other postulates as investigated in that belief revision and update literature. So I go quickly over the existing semantics because I would like to take you to the last part very quickly. So there are a lot of them. Well-founded, which basically compute fixed points, choose some violation, only look at the idea, choose some violated constraints and update by one of the actions in the active part and iterate that. That's compatible both with the permission and the obligation reading. Then the founded has a different idea, which goes with the permission reading. So the idea is that update actions alpha belonging to the repair should be supported by a constraint. So every action in the repair should be supported, which means that the constraint would be violated without alpha. So the definition says alpha, for every alpha in the repair, there should be an active constraint such that alpha appears in the repair part. And if I update the database by something less, so if I drop alpha from the repair, then I would violate that constraint. So alpha is responsible for the repair of that constraint. Yeah? That is the intuition. I skipped the example. The grounded repairs are nothing but a generalization from singletons to sets of repairs. Then I go to the last one, justified repairs, which are, well, I don't expect you to read this. They are fairly complicated. They haven't been further elaborated or taken up in the literature, I would say, but people usually say, oh, they are very complicated. What I only want to retain is that it does not, so the active part of the constraint cannot be, you cannot have normalization, singletons on the right side, and that indicates an obligation reading, and that's also supported by the explanations Caroprese and Toshinsky gave. Now, and that's my favorite sport, sort of analyzing things in dynamic logic. And specifically in dynamic logic of propositional assignments. So that's dynamic logic where the atomic programs have been replaced by atomic assignments, making P true, making P false. And that's exactly what fits what we need for these active constraints. Modal formulas, programs, you can actually, by these programs, capture the standard programming constructions, such as the while. Now, the semantics of that logic of assignments is based on classical valuations. So you don't need these complicated crypty models. You can eliminate the Kleene star, and therefore all dynamic operators. And the complexity is quite interesting as compared to dynamic logic, propositional dynamic logic, PDL. How can we capture repairs in that logic? Well, first of all, we have an active constraint, and we can associate a program of dynamic logic quite straightforwardly. What does the program do? It checks, is the constraint, the static part of the active constraint, is it violated? And if so, if not violated, the program fails. If it is violated, then there's a non-deterministic choice of one of the update actions in the repair part, and that action is performed. So with that encoding, you can capture both these founded repairs and the justified repairs, and I believe all the others, but we did not do it in a publication 2019. It also needs some copying of variables, but basically it is a rather simple encoding in dynamic logic. And finally, it also sort of naturally leads to another definition of what we call the dynamic repair. And that is obtained, so the dynamic repair is a program which makes us go from some database to an updated database. And what does the program? Well, it's a while loop. It checks whether is there a violated constraint, and then pick out one of them and execute the active part. So this comes with an obligation reading. It generalizes well-founded repairs. It repairs a bit more, but it's a matter of debate whether this is really better. And it's p-space complete. So here is an example, but I will skip it to go a bit faster. We can have a lot of reasoning problems that we can, in this way, capture within dynamic logic, and it's a sort of Hilbert-like program. We do the reasoning not in the meta language, but in the language of dynamic logic in order to prove properties of repairs. Finally, that tool of dynamic logic also allows us to capture these event condition action rules. Remember, they had an event. When an event occurs and the condition is satisfied, some action is triggered. And people typically say that they are too expressive in order to be analyzed by some logical tools. And that's why people restricted to these couples and not triples. But, well, here is a proposal where we can have, and I will only look at this, we can add this event part by means of a Boolean formula, which is built from assignments. So that's a bit non-standard, but it means if the event is that somebody got, sorry, this is a functional constraint. So if the last transaction was that the employee got moved to department 1, and it is violated that an employee should not be in 2 different departments, then he should be withdrawn from the 2nd department. And the other way around, if he was moved to D2, he should go away from D1. So you can
just a quick notice here, Andreas, you've got 4 minutes left.
Yeah. Okay, so I will have to go. So I will only go quickly. You can adapt the models by adding a sort of history, and again capture all these things in dynamic logic of assignment, which is, this is still some tentative work, but it looks like also these event condition action rules can be captured. And now I move to the last part, which is how can we import these ideas to description logics. So we have these, there are some differences, but there are some things that are in common. We have these TBoxes which are non-contingent, typically stable in time, so they play the role of integrity constraints, although it's not exactly the same. While the A-boxes are contingent, change more frequently, and ideally T-box and A-box should be consistent, and not the A-box should infer the T-boxes as it in databases, so that's a small change. And typically, given that the T-box is stable in time rather, this is caused by changes to the A-box. So why not look at active T-boxes and let them play the role of active integrity constraints? That is the idea. There are many other approaches actually how to repair inconsistent knowledge bases, but it seems maybe we overlooked something, but not too much people or nobody looked at preferences between possible repairs, which was what these active constraints do. So how can we import that idea? Well, if we have that example T-box, which is inconsistent with the A-box, then we could extend the T-box to an active T-box and say, for example, if a father is somebody who is male and a parent, and if this is violated, we should add that he gets male and he gets a parent. And when only jiggling child included in having no siblings is violated, then we should delete only child. Yeah, that leads to that repair. Alternatively, we could also say if the first father should be male and parent is violated, then he's not a father. And if only child implies no sibling, then we should delete that that concept. So that leads to a different repaired A-box. Yeah, and the challenges when doing that move to description logics, there are at least three. First of all, these A-boxes are not simply databases, just sets of propositional variables. We have concept constructors, complex concept. So these atomic update actions usually will not be sufficient. Second point, we have closed world semantics as opposed to open, we have open world semantics, and then this means satisfiability checking should replace model checking. And then we have a choice between removing or forgetting concepts. So that is also something to consider. And I only list here 3 papers, well, 2 papers and a PhD thesis of Christos, where there were different proposals, one syntactic, one semantic, and the semantic one had a dynamic extension of the description logic ALCO. So it looks like I'm in time. In summary, what did I do? My main point was not to go into the details of the different proposals for semantics of active integrity constraints, but rather to re-examine the intuitions behind them. And then we had that permission obligation distinction, which gives you very different behaviors. And I believe the obligation reading is underrated. And then that principle of extensionality, which might lead to, so remember that slogan in philosophy, no entity without identity. When are 2 active constraints the same, 2 sets of active constraints the same, that deserves to be investigated more. And second, I have looked at it through the lens of dynamic logic, which led to the introduction of dynamic repairs and also to a proposal for how to capture these event condition action rules, which go beyond active constraints. And finally, I have only sketched how repairs could be done better based on active T-boxes. I refer to these 2 papers, 2017, 2018, in presented at the description logic workshop, but that's certainly not the last word. So if we look ahead a bit, what are the good postulates for database repair? That's an interesting question, I believe. And can we get, on a more practical term, can we get better complexity results for repairs based on active TBoxes? I didn't talk about it, but it is pretty complex to do so. And finally, how can this be applied to defeasible description objects? Thank you for your attention.